Zeno's famous paradox tells us that it's impossible to overtake a tortoise. Run as fast as you like. By the time you reach the tortoise's initial position, it'll have moved forward. Reach that second position, it'll have moved forward again. To overtake a tortoise, you need to travel to its previous position infinite times. Each of those steps is shorter than the last, but there are still an infinite number of them. There are a few problems with this paradox, but one is that it assumes that space is infinitely divisible. This is not true. As your distance to the tortoise becomes unthinkably small, there arises a quantum uncertainty in your location. Get close enough to it, and this quantum blurriness means it's impossible to say whether your location is really behind or in front of the tortoise. We talked about this recently when we discussed the de Broglie wavelength. This, and more formally the Heisenberg uncertainty principle, describes the smallest distance for which an object's location can be meaningfully defined. The tiny Planck constant at 6.63 by 10 to the minus 34 joules seconds sets the scale of this quantum blurriness. So it also sort of defines a pixel scale to reality. In many ways, it defines the divisibility of the quantum world. In fact, the Planck constant appears in essentially all equations that describe quantum phenomena. The Heisenberg uncertainty principle and the de Broglie wavelength, but also the Schrödinger equation, the energy levels of electron orbits, and importantly, the relationship between the energy and frequency of a photon. It also sets the size of the Planck length, which is, hypothetically, the length below which the concept of length loses meaning. It may define the scale of quantum reality, but the influence of the Planck constant can be seen even on our scale. For example, along with the sun's temperature, it sets the color of sunlight. If the Planck constant were 25% smaller, the sun would be violet, all else being equal. In fact, the mystery of why hot things glow the color that they do led us to discover the quantum universe in the first place. Science fact: everything in the universe glows with the light of its own internal heats. Heat is just the energy in the random motion of particles comprising an object. Accelerated charges produce electromagnetic radiation, light, and so an object made of jiggling charged particles, like electrons and protons, glows. The hotter an object is, the faster its particles jiggle, and so the average frequency of the resulting particles of light, of photons, increases with temperature. This average frequency defines the color that we see. The sun is yellow because its 6,000 Kelvin surface produces more photons in the greeny yellow part of the electromagnetic spectrum than anywhere else. The blue supergiant star Rigel is 12,000 Kelvin, and so it pumps out lots of high-frequency blue light and even more ultraviolets. Your temperature is around 310 Kelvin, so your heat glow is mostly in low-frequency infrared photons. It was Sir Isaac Newton who first analysed this heat glow in the 1660s when he used a prism to split sunlight into its component colours. But he didn't realise that the relative brightnesses of those colours held the key to the quantum world. By the late 1800s, the distribution of brightnesses with frequency produced by hot objects had been mapped in careful experiments that blacked out anything but the glow of heat. The resulting blackbody spectrum looks like a lopsided bell curve. However, the deep physics behind this shape remained a mystery. The key to unlocking the mystery lay in finding a mathematical description for the blackbody spectrum. At the beginning of the 20th century, a couple more Brits, Lord Rayleigh and Sir James Jeans, attacked the problem with a relatively new idea called the equipartition theorem. It states that an object's heat energy will end up jiggling all of its particles in all the ways that they can be jiggled. In physics speak, at equilibrium, energy is evenly spread between all possible energy states. This simple idea allowed our good Englishmen to figure out the frequencies of the photons produced by all of this thermal motion. The resulting Rayleigh-Jeans law described the blackbody spectrum perfectly. For low frequency, infrared light. But for higher frequencies, like visible and ultraviolet, it predicted brightnesses that were way too high. Worse, it predicted that the intensity should eventually approach infinity as frequency increased. It paints the crazy picture of a universe full of infinite extreme energy gamma radiation. This appears not to be the case. This was called the ultraviolet catastrophe. It was catastrophic because it meant that something was fundamentally wrong with the classical physics that went into the Rayleigh-Jeans law. The problem turned out to be that in classical physics, everything can be infinitely divided. There's no smallest anything. The Rayleigh-Jeans calculation allows particles to vibrate with any amount of energy, all the way down to infinitesimally tiny wiggles. When they tried to mathematically distribute heat energy, to equipartition it across possible energy states, way too much energy got packed into the countless, very tiny energy states at high frequencies. Mathematically, Rayleigh and Jeans were chasing Zeno's tortoise, infinitely dividing the smallest remaining energy states, and so never ever finding an end to them. German physicist Max Carl Ernst Ludwig Planck resolved the catastrophe almost by accident. While searching for a new mathematical approach to deriving the blackbody spectrum, he needed some sort of math trick to count those supposedly infinite energy states. In what he described as a moment of desperation, he tried something pretty silly. He decided that those particles could only vibrate with energies that were a multiple of some minimum energy. He quantized the energy states. He set this minimum energy to be the frequency of a particle's vibration times a very, very small number, a number that had yet to be measured. That number became the Planck constant. It was a move similar to smushing your hands on the keyboard when your computer freezes. But it worked. It allowed Planck to equipartition energy in a way that solved the ultraviolet catastrophe. Why? Because it limited how much energy those high-frequency vibrations could hold. Planck's new equation described the shape of the blackbody spectrum exactly across all frequencies of light. It became Planck's law. Now, Max Planck didn't originally think that these quantized energy levels were real. It was supposed to be a math trick. He expected his new constant to turn out to be zero, which would mean no interval between energy states, no quantization, no minimum energy. In that case, the Planck constant would have cancelled out in the final equation. But it didn't. The Planck constant is firmly entrenched in the Planck blackbody law. Energy quantization is real. Now, the actual value of the Planck constant still had to be measured, but given a mathematical form for the blackbody spectrum, it was possible to do this just by varying the constant until the Planck law matched the observed spectrum. But once you know the Planck law and an object's temperature, you can calculate the Planck constant just by finding the brightest part of an object's heat glow. For example, by observing the colour of the sun. As usual, it took Albert Einstein to fully understand the physics behind Planck's strange quantized vibrations. Einstein realized that it's actually light that is quantized. Those little vibrating particles do have quantized energies, but it's because they can only gain or lose energy by absorbing or emitting one particle of light at a time. And that light comes in indivisible energy packets. Planck's discovery was the clue Einstein needed to hypothesize the existence of the photon, part wave, part particle, carrying a quantum of energy equal to the now familiar frequency of the wave times the Planck constant. Einstein proved this through the photoelectric effect. It got him the 1921 Nobel Prize in Physics, shortly following Planck's Nobel of 1918. These discoveries sparked a frenzy of sciencing that led to the quantum revolution of the 1920s. And that little number that Max Planck came up with in his moment of desperation, the Planck constant, remains at the heart of all things quantum. but not just quantum. By defining the shape of the blackbody spectrum, the Planck constant can be read in the colour of the sun and the stars, in the brightness of the different colours of the rainbow, and combined with a small handful of other fundamental constants, it governs the behaviour of everything in this spacetime. Thanks to the Great Courses Plus for sponsoring this episode.